is also a scary, famous person from Portland. His name is Zach Babb, and he's going to tell you how to build a computer in your browser, which is kind of amazing.
So I'm certainly not scary, and I'm certainly not famous, but thanks for that introduction. My name is Zach Babb. I'm the lead mobile engineer for Globe Sherpa in town. I had a bunch of stuff I wanted to prepare today, but I didn't quite get there because we launched beta of our app yesterday, so I'm a little behind. But I'm going to do my best to present what's at this point more of an idea than anything, but there'll be a little demo at the end. But I'm naming this computer in your browser the von Neumann 51. It's an extension on a programming assignment I had in college, where we programmed in a Java-based computer called the von Neumann 50. So this is extending that project into a browser. But first I want to go a little bit into the motivation for the project. The previous speaker mentioned the von Neumann Bottleneck, which is, I think, a great segue into not only this picture of John von Neumann and his vacuum tube computer from the 1940s, but also sort of the motivation behind trying to build a browser in a computer in your browser, why that's an important thing to go after. And that's that when I'm looking back on sort of how I learned, and I hope everyone here reflects on how they learned programming, we get to this stage where we understand way more than someone new to programming. And we mentioned things like the von Neumann bottleneck as though everyone knows what it is, and I'm sure we all know what it is. I didn't until this morning when I was reading about von Neumann. And it's actually a distinction between von Neumann's architecture and Harvard's architecture. The von Neumann architecture has the stored program and your data both in the same memory. So the von Neumann bottleneck is what happens when they share the same bus, and you are fetching a program instruction and trying to fetch memory at the same time, but you can't because they have the same bus. But even going through that, you have to realize that not everyone knows what the term architecture means, and not everyone knows what the term bus means, and not everyone knows what the term stored memory means. And there's a lot of variation on the way we use those terms. And that's sort of what this project is going after, is to sort of build from the ground up knowledge of all of these terms that you just sort of pick up along the way. And so about picking things up along the way, I want to talk a little bit about how I pick things up along the way. And, you can't even see the middle one. That's my favorite. But did anyone use Logo when they were a kid? That was my favorite thing. I used Logo in third grade, And the thing I loved about Logo is it had this really simple language, right? And the way I learned it, it was a little turtle in the middle, right? And you would tell the turtle, write 50. And you wouldn't have to really worry about what you meant by 50, right? 50 was the number of steps that the turtle went, And then you put the instruction in, and you saw what 50 looked like. And you could build up from there, right? You didn't really have to be careful as you were learning about what you meant by 50, right? And that's where we get into web standards now, where, 50 means 50 pixels. Or I'm a mobile guy, so you have density-independent pixels, right, if you're in a retina display. And there's a lot of things you have to be careful about. On the left is a picture of HyperCard. Anyone use HyperCard back in the day? Yeah. So these were great tools, and the reason they existed were half, to help people learn, but half because that's all computers could do back then, They couldn't do all the fancy stuff that we're doing right now. I mean, they could do plenty of fancy stuff. They put someone on the moon. But these were the tools that were just available, and they were accessible. They were accessible to youth who were learning how to program. And I think that there's a lot of stuff that's still accessible, but what I'd like to see is something that is accessible simply because it's bad, it's slow, it's old, like that. There was constraints that you had to live within when you were learning these things, and it made things a lot easier to learn. And then on the right is just a snapshot of good old DOS. I don't know how many of you remember this screen from trying to install Quake when you were a kid. And making sure you had. I still don't really know what this means, but I remember seeing it as a kid and being like, I want to know more about that. So I guess what I'm trying to do is in the browser, and what I hope some of you might want to try and do with me, because I can't do it on my own, is rebuild this version of computing, this time frame of computing, when things just weren't so fast and weren't so powerful, so that other people can try and learn along the way. And let's see. So more of the motivation came from when I started taking CS in college, and I learned about deterministic finite automata and started going through logic circuits and things along those lines. I was a physics major, so I did a lot of analog circuitry, which is different than digital circuitry, right? And I remember sitting in class learning about finite automata and thinking to myself, oh, you know, a computer is just like a really complicated version of that. You know, for those of you who haven't seen a map like this, in the top picture there, you have all of these states, right? And the zeros and ones are input. And what a DFA does is it reads a string of input, and it moves to different states. So if you can follow the arrows around, if I put in the string 101, I would end up back where I started. And the thick circle there means it's an accept state. So you can imagine a machine that has, two buttons to input things, zeros and ones. And on the right-hand side, has a red light and a green light. And if you end up back at that bold state, the light turns green. And if you end up back at or at any other state with a string of ones and zeros, the light turns red. And that could be like an actual physical deterministic finite automata. And as we were learning this, we were learning about circuits. For those of you who might not be familiar, the circuit on the left is a full adder. It contains 3 different types of logic gates. The 2 at the top are exclusive OR gates. The 2 at the bottom to the left are AND gates, and then there's an OR gate. And what it does is you have 2 bits, A and B, and those get added together through an exclusive OR, which then gets fed in with a carry-in bit. The carry-in bit is what makes it a full adder. That outputs the sum, which is 0 or 1. And then the carry-out is you add 2 ones together in base 2, you have to carry a 1. So that's what that bit is. You can actually build these circuits. So logic gates are built out of transistors. You can actually build them out of diodes if you really want to. One of the things when I started working on this project was trying to figure out just how deep into physics I wanted to go, So digital circuits nowadays usually use 5 volts, 4.5 volts as actually, most of them use them as a 0. They're inverted, but I like to think of it as the high voltage is a 1 and the low voltage is a 0. And so if you had 2, let's take an AND gate, for example. If you had 2 high voltages at the input on the left, it would give a high voltage out on the right? And you could go into how you would build that circuit out of transistors, how you would give it a power supply, how you would do that. But I'm not going to do any of that, because that's more physics than it is computing. But you could, and that's actually what I endeavored to do first. On the right-hand side is a D flip-flop. Flip-flops in general are the way you store bits. I was hoping to have these dynamic, but I didn't have time. But the part on the right, basically the Q, if you store a 1 in it, it just always outputs a 1. Right? And so that's how you store memory. And basically, computers are just, or the memory in computers are just really long strings of these flip-flops. And they switch between 0 and 1 based on what you want to write, all that sort of good stuff. And so when I was learning all this stuff, I had the brilliant idea that I would go to some electronics store, I would pick up, some AND gates, some OR gates, and I would just build a computer from scratch, right? Like, that couldn't be too hard. Other people have done it. And so the first thing I did was try to build a deterministic finite automata, not too different from the one that's up at the top. And it ended up looking like this. So this might be, if you had to put numbers on it, it would be like a 2-bit computer that ran at something like 0.01 hertz. So building that up into something that might be useful was not really all that practical for me at the time. But I did it. It only cost like $90 in electronic stuff because I didn't know what I was doing. And so I decided to take sort of a pivot and change direction if I wanted to build a computer from scratch. Still, it was a lot of fun. By the way, what this does is the two blue buttons down at the bottom that are wired up, if you press them in the right sequence, I think it was like left, right, then a green light would turn on. And if you press them in the wrong sequence, a red light would turn on. That's all that does. Oh goodness, that looks terrible. Can you guys see that at all? What's the hotkey for that? Whoop. My option key is broken, so I have it remapped to caps, but it doesn't seem to be working right now. Let me unplug and see if I can do this. Oh wait. Nope. Oh no. Do they deprecate it? All right. We're going to get there real quick.
Just go to accessibility, convert colors right in there.
All right. Thank you, everybody. All right. So, this at the same time I was sort of messing around with DFAs and electronics, I was also starting to learn JavaScript. So the very first real stuff I started working on was in Objective-C because I really like iPhones, so I started learning that. And then I migrated over to JavaScript after a while, and I really was enamored by sort of the ease by which you could learn object-oriented programming and start to use it usefully. It's really quick to just sort of get it up and running and on screen. That's one thing that I also sort of lament about people learning nowadays. If you want to go after iOS development or Windows development, you have to download these huge IDEs like Visual Studio and stuff like that. I mean, you don't have to, but that's what pops up when you Google how to start, But JavaScript, you can open up Nano in Bash, and start typing an HTML page with some JavaScript in it and get it up and running and actually in your browser running, I think that's really cool. So this, though, I will never speak disparagingly about anybody trying to teach anybody something about programming. But if you guys will indulge me real quick while I point out some of the things that are an opportunity in this page, just know that I'm not speaking ill about anybody. I just want to sort of take people through what I came to JavaScript. So this is the very first thing that you see if you go to Code Academy and you look for object-oriented programming in JavaScript. This is their example, right? Right away, the classic object example is a person, so they don't want to use the classical and they want to use a phone book. That's fine, except that we're 3 years away from no one knowing what a phone book is anymore, so I don't even know. But let's just go through everything that's encapsulated right in these 9 lines of code. So very first off, you have the keyword var. Right? Now, if this is your first programming language you're being exposed to, do you know that indicates it's a variable? Do you know it's even a keyword? Do you know that this is something that establishes phone book entry as something? Right? Then, and I don't know about you guys, but when I first started learning programming, the capitalization or no capitalization of what and when to it still doesn't make a lot of sense to me. When do you capitalize? Do you have to capitalize, right? So you have the camel casing. And then you have an object literal that is encapsulated by curly braces. Now, JavaScript overloads curly braces, right? It's also how you put functions and loops and all that sort of good stuff. And it's an object literal. None of this is explained to the person who's learning JavaScript, right? It's just bam, right there. Next, you have dynamic dot notation in JavaScript. So you're adding properties to this object that you already created, although it's not even really clear that you've created an object. You're establishing these properties with values, and then you also have a property that ends up being a function. But what does a function do? You have another object, console, but you don't know what the console is. you have the keyword this inside a function that is attached to a property, and anyone working in JavaScript knows how much a pain this can be when you're first starting out. And then finally, you call this function. Sure, okay, what does it do, right? It's not at all clear what it does. It writes something to the console, maybe, if we know what log does. And then my favorite is the whole string, right? So like you have an overloaded plus operator for string concatenation, and you have to have taken an intro to computer science class just to understand what overloaded plus operator for string concatenation means, right? And so you need to have a basis even to understand what you don't understand about what's going on here. And so what I'm trying to do is build up, a lot of this stuff I got when I was learning, and I could do it, but I didn't really understand it till I started building. In a class we built a parser, we built an interpreter, built your own programming language, and there's extreme value in that, right? And you start to understand like, why is there white space in between the plus operators? Is it necessary? Is it not necessary? Why do the lines terminate with a semicolon? Why do some lines not terminate with a semicolon, right? All of these questions you have to sort of ask yourself. And so that's what I wanted to do in the von Neumann 51 project. So the way it works, or the way I sort of envision it, is a series of tutorials that you're presented with a project, right? Just like you would pull down a project from Git. You would be given a template that you put your code in, and I'll show you sort of the first one. Oh gosh, I gotta re-invert now. Yep. Okay. So, and the tutorial goes through all this stuff, and it's blurry, and I apologize for that, but it's just an HTML page, right? So you start learning about tags, you start learning about how JavaScript interacts with the tags. We have a little bit of CSS in there too. And so a learner here and I like going through pains and explaining what people are seeing there. And so that's part of the idea, right? But there's a lot going on here. And I think that's fine. It's fine to have a lot going on here as long as you're willing to explain what's going on. But what I like about this is somebody can take this, they can double-click it on their computer, and it pops up in their browser, right? And then they can add code to it, and they can see what that does. Or they can break it. That's how most people learn. So anyways, this is just like an example, and it's probably really bad, but it's a starting point. And what I want to show you guys now is just a little demo of what we're going for, and then put it out there, I guess, for questions and try and get you guys on lunch or to lunch on time. But this is what the first tutorial looks like when you first start. So we have this one gate. It has two inputs. It has an output, and it doesn't do anything. It doesn't have any logic to it. And so what the tutorial goes through is building the logic for the gates, right? It exposes an API where you can add, true, false. There's if statements, all that sort of good stuff. And what you eventually build in the tutorial are these 4 logic gates, right? And what I like about them is that they work, right? So if you change everything to a 1, then it outputs a 1. If you change the OR to a 1, that goes. And so from this, right, we would take these gates, and the next tutorial that I'm working on right now is you build the full adder circuit and the D flip-flop. So you build those circuits. And then in the next one, you would build like a multiplexer, something along those lines. And you would build the components for a computer up until you actually have the computer in your browser. And that's what I thought I would be further along with today, but I am not. But what I do have for you is sort of a little bit of the end goal, which is the von Neumann 51 prototype. So the von Neumann 51 is a 4-bit instruction set computer, of which I have written 3 instructions, which I'll show to you right now. And that's a little blurry towards the top. Let's see if that looks any better. All right, so we have 4 registers, and one of the operations is assignment. And what you see over on the right is actually it's parsed the statement, it's turned it into byte code. It's 16 bits, 2 bytes long. The first 4 bits are the instruction. This is assignment, so let's see. The second 4 bits are the destination register, so is that right? Yeah. And then the next 4 bits are the number that gets assigned to that register, and then there's trailing zeros to make sure that it's 16 bits long. Let's see. Let's just give another register a number. And then we can add. And you can see that the instruction has changed. We have addition now, and we're adding the, let's see, so it goes the destination registers, 2, and then the first source register, which is 0, and then the second source register, which is 1. And so the idea is when you build the multiplexer, right, it would take the first 4 bits and wire up the registers in the configuration you need in order to actually execute the instruction. And then for addition, you would have 4 full adders linked together so that you could do 4-bit addition. And we would go through the process of how that all works. And then, I'll show you the last instruction, which is put reg2, which has the value 10 in binary. And so what eventually I want to build up to is getting into sort of data types, right? So we have the binary representation of 10, right? But if we do put to the display, we don't actually want to see the binary representation of 10. We want to see the decimal representation of 10, right? So we would have to actually build the components that convert back into decimal and output a number and things along those lines. So that's sort of where I envision it going. And then once we have all 16 instructions, we can use them to build more complex things. Maybe add a 5th bit, start adding new instructions. Anyways, it's something that I think we can grow upon, but it is kind of a very nascent idea. But that's it. And I'll take questions for 4 minutes, or if everyone wants to get food, then that's cool too. And thanks for letting me talk with you guys.